Hi, I'm Steve.
And I'm Dom, and we're going to explain how to solve the stable roommate problem using Irving's algorithm.
The problem is that for an even number of people, each person needs to be paired up with another person in the group. There are obviously many different ways you can pair people up, but the aim here is to find a set of matches that make everyone as happy as possible. Especially Ralph. We love Ralph. This is called a stable matching.
Now, the fancy definition of stable matching is for any two people that have been paired together, there must be no other possible matching that both people would rather be in. In order to solve this problem, we're going to need a list of preferences from everyone involved that ranks everyone else in the group. As we mentioned, the solution to this problem is Irving's algorithm, and that can be broken down into 3 steps. The first step is very similar to the Gale-Shapley algorithm, which is used in the stable marriage problem.
The first step is where each person in the group makes their initial proposals to the others. What we have here in the matrix is each person's list of preferences. For example, Ralph's first preference is Penny.
I wish I was Ralph's first preference.
Don't we all? Ginny is Ralph's last preference.
Ralph starts by proposing to Penny. Penny currently has no other proposals, so she automatically accepts Ralph's proposal. Who wouldn't? Penny then proposes to Oliver, who accepts, but now Boris also proposes to Oliver. This is a problem because Oliver now has 2 proposals. When this happens, the proposee gets to pick which match to keep based on their preferences.
In this case, Oliver prefers Penny to Boris, so he rejects Boris's proposal. When someone rejects a proposal, the proposer is crossed off their preference list, and symmetrically the proposee is crossed off the proposer's preference list. Here, since Oliver rejects Boris, Boris then has to cross Oliver from his list, because that match can no longer happen. Boris then proposes to his next highest preference, Tammy, who accepts. Next, Ginny proposes to Ralph, which he accepts because he has no current proposals.
Other than mine.
Oliver then also proposes to Ralph. Since Ralph now has 2 proposals, he has to reject someone, as well as Dom. Oliver is high on his preferences, so Ginny is rejected. Gutted. As soon as someone's proposal is rejected, they are always the next person to propose, so Ginny proposes to Boris, which he accepts.
Next up, Tammy proposes to Penny. Penny obviously prefers a current partner, because it's Ralph.
Yeah, it's Ralph, isn't it?
So Tammy, undeterred, moves on to, surprise surprise, Ralph. Ralph also rejects her, as he prefers Oliver. So third time lucky, she proposes to Ginny, who accepts. Once everyone's been proposed to, and they've accepted their proposals, we can move on to step 2.
Step 2 is the shortest step of the algorithm. All it does is rule out any matchings which are worse than the ones people already have. So all you have to do is look right in the matrix.
For each person, we need to look at who's proposed to them. We then cross off anyone in their list who's ranked lower than the current proposer, making sure to delete their matches symmetrically.
So here, Ralph is being proposed to by Oliver. Tammy and Ginny are lower than Oliver in Ralph's preferences, but are already rejected. Penny is being proposed to by Ralph, so Boris is rejected. Boris is being proposed to by Ginny, who is the last person on his preference list, and since no one is lower than Ginny, no further people have to be rejected. Ginny is being proposed to by Tammy, so Penny and Oliver are rejected. Oliver is being proposed to by Penny, so Tammy is rejected, and Tammy is being proposed to by Boris, but Oliver has already been rejected.
From now on, we will call the lists of available matches for each person their reduced lists. We now need to check that the table is stable, and to be stable it must satisfy these 4 rules. For any 2 people, P and Q, if P is at the top of Q's reduced list, Q is at the bottom of P's. For example, Penny is Ralph's first preference, but Ralph is Penny's last preference. The second rule is that everyone less preferable to P's current match is rejected. This is simply what this step does. It rejects all of the least favourable matches. The third rule is that all rejections must be symmetrical. So if Tammy rejects Oliver, Oliver must also reject Tammy. The final rule is that no reduced list is empty. Otherwise, that person would have no options left and be sad.
If we found that the table wasn't stable, then we would know for certain at this point that no stable matching exists. However, even if we do have a stable table, we still can't guarantee that there is a stable matching to be found. Now we can move on to step 3.
Step 3 is probably the most complicated of the 3 steps. It involves creating cycles of people based on their second and last preferences in their reduced lists. This sounds complicated, but we'll do our best to explain it to you.
For this step, we can start with any person that has at least 2 people left in their reduced list. For example, we can start with Ralph, because we love Ralph. We'll construct a table with 2 rows, P and Q.
We then go through in a zigzagging pattern according to 2 rules. The first rule is that a person in Q below any P is that P's second preference. So for example, Boris is Ralph's second preference. The next rule is that a person up and to the right of a queue is that queue's last preference. So for example, Boris's last preference is Ginny. If we follow this through, we'll see that Ginny's second preference is Tammy, Tammy's last preference is Boris, Boris's second preference is Ralph, Ralph's last preference is Oliver, Oliver's second preference is Penny, and Penny's last preference is Ralph.
And we do this until the same person appears in a row twice. So for example, Ralph appears in row P twice.
Yeah, he does.
We go through the table now that we just created, rejecting the pair of Q and their last preference. So Boris and Ginny reject each other, Tammy and Boris reject each other, Ralph and Oliver reject each other, and Penny and Ralph reject each other.
If at any point someone's reduced list becomes empty, then no stable matching exists. If there is anyone with more than one person in the reduced list, repeat this step until everyone has only one person left. Then you have a stable matching!
Yay! In our example, Ralph matches with Boris,
Aww.
Ginny matches with Tammy, and Penny matches with Oliver. This is our final stable matching.
To investigate the time complexity of this algorithm, we'll need to take a look at the pseudocode, looking first at step 1. We'll first assume that accepting and rejecting matches takes constant time.
Step 1 has a while loop for as long as there are unmatched people. Everything inside this loop is just constant time because only if and else statements are used and only accept and rejects are used. In the worst case, all but the lowest preferences get rejected, meaning n squared minus n all over 2 rejects are used. So the big O of this step is n squared.
In step 2 there is a for loop for every proposal, and for each of those proposals all of the less preferable people are rejected. In the worst case, all of the first preferences are accepted, meaning there are n squared minus n rejects, making it in big O also n squared.
In step 3, you traverse the second and last preferences of certain people. The worst case would involve the most matches being left unrejected from the last steps, so more has to be rejected here. It couldn't be either of the situations from the previous worst cases because if all the first preferences were accepted, step 2 would have rejected everything else, and if all the last preferences were accepted, step 1 would have rejected everything else. So the worst case is roughly half the grid being unrejected. However, n squared over 2 steps is still big O of n squared.
Since all of the steps are big O of n squared, the algorithm itself is also big O of n squared. Thinking about this more simply, each cell of the n squared size matrix is rejected only once, meaning the overall complexity was always going to be n squared. So that's all from us. We hope you enjoyed this tutorial and you've understood the algorithm now. Also, I hope you appreciate our love for Ralph.
If there's anyone called Ralph in your life, make sure you tell them that you love them and that you appreciate them.
If you've got any comments for us or if you have any questions, just feel free to leave them in the comments. Until next time, we'll see you later.
Thank you!